Hello students, welcome to Vihira Academy. I am your educator Dr. Hina Devnani and today we are going to study chapter number 10 of 10th standard science, that is light, reflection and refraction. This is the second part of the chapter. We have already studied the first part in which we have studied reflection of light. Today we are going to study refraction of light. So let's start with our first topic, refraction of light. What is refraction of light? When light travels obliquely from one transparent medium into another transparent medium, it gets bent. We have seen in reflection of light that the light gets bounced back. But here the light is not getting bounced. Instead, it is entering the second medium and it is getting bent. This bending of light is called as refraction of light. You can see in this image, here the light is incident on a surface and from here it is getting bent. So this bending is known as refraction of light. Now this bending can also be of two types. Either the light can bend towards the normal or it can bend away from the normal. Suppose if this incident ray and this refracted ray are interchanged. So the refracted ray becomes incident ray and this becomes refracted ray. So you can see that this has moved away from the normal. Now if this is incident ray and this is refracted ray, you can see that the ray of light has moved towards the normal. So if the light travels from a rarer medium, this is a rarer medium, that means it has less density as compared to this. So if a ray of light moves from a rare medium to a dense medium, it will bend towards the normal. If the light is traveling from a dense medium to the rare medium, it will bend away from the normal. So this is refraction of light. Now we have to study refraction of light in detail by performing an activity or an experiment of rectangular glass slab. Here I have shown the image of a rectangular glass slab. As this is transparent, we can easily perform experiment of refraction on this. What happens when we perform this experiment? A ray of light passes through a rectangular glass slab and it gets bent twice. As you can see, this is a cuboid, so it has two edges. So once the ray of light will be bent at this edge and then the ray of light will bend at this edge. So here the ray of light bends at two surfaces. First, the ray of light will be incident, then it will become refracted, and then when it comes out from here, it will become emergent ray. The ray which is emergent will be parallel to the incident ray. Suppose if incident ray is coming from here, it is getting refracted and the emergent ray is coming from here. The emergent ray and the incident ray will be parallel to each other. The only difference will be emergent ray will be displaced through a distance. So let us study this with the help of a diagram. Now before studying this diagram, we need to study the activity that is given in your textbook. What the activity says, first of all, what you need to do, take a white sheet of paper and then you have to fix that white sheet with the help of drawing pins. Now you have to place the rectangular glass slab over that sheet. Then you need to draw an outline. So this kind of outline will be drawn for the glass slab. Now you have to take 4 pins. You can take thumb pins, you can take all pins. These 4 pins you have to place at two places, let's say A and B. You have to place these 2 pins over here. Now what you have to do, you have to look for the images of these pins. Look from this side where you have placed the pins. Look for the images and you will find that the images are somewhere here at C and D. So here the images will be formed. Here you are keeping the objects, that means the pins A and B, and you can see the images. Now what you have to do, remove the pins, put points over there wherever you have placed the pins, remove the slab and then join all the lines over here. You have to join A and B with the surface. You have to join C and D with this surface. A and B will be joined with E and C and D will be joined with F. Now you have to join E and F. Then you need to draw 2 perpendiculars on both the surface. One perpendicular will be N1 and N2, that is the normal, Another perpendicular is n1 dash and n2 dash. So you have drawn everything. Now let me tell you what all things are present here. This is the first medium, that is air. This is the second medium, that is glass. Again, this is the first medium, that is air. That means air is the rare medium. It has less density. Glass has more density. So when the ray of light will go from air to glass, it will move towards the normal. You can see this EF. This is the refracted ray and it has moved towards the normal. Suppose if this glass slab was not there, the ray would have gone like this, straight. But it has moved towards the normal because it is present in glass. Here you can mark I, that is angle of incidence. Here you can mark R, that is angle of refraction. Now this refracted ray will again get refracted at this point. Why? Because here again the medium is getting changed. The glass was denser medium, the air is rarer medium. So the ray of light, when it gets refracted, it will move away from the normal. You can see here it is going away from the normal. This angle is known as angle E, that is angle of emergence. Now when this ray comes out, just draw a straight line over here. Then draw a straight line from AB, imagining that the glass slab was not present. If the glass slab is not present, this will go like this, straight away. Now you can see that this ray, which was the actual ray in the absence of glass slab, is parallel to the emergent ray that is produced because of the presence of glass slab. These both rays are parallel to each other. Only differences they have is this. This emergent ray is actually laterally displaced and this displacement is denoted with a small d. Small d represents the lateral displacement. So this experiment actually tells us that diffraction is based on the density of the medium. It is also based on the speed of light. The speed of light in air will be different. The speed of light in glass will be different. And because of that differences in speed of light, you can observe refraction. This experiment is very, very important for the board exams. Now, if we have studied refraction, we should also study laws of refraction of light. There are two laws of refraction of light. First law is incident ray, refracted ray and the normal to the interface of true transparent media at the point of incidence, they all lie in the same plane. This law is similar to the law of reflection of light. What does the second law says? The second law says that the ratio of sine of angle of incidence to the sine of angle of refraction is always a constant. For the light of a given color and for a given pair of media. You have to remember this, that it is for a given color and given pair of media. This law can also be called as Snell's law of refraction. This is the formula of Snell's law of refraction. Sin I upon sin R is equal to constant. Now what is this constant? This constant is actually the value of refractive index of the second medium as compared to the first medium. Now we are going to study in detail what is refractive index. Refractive index. Refractive index is a very important physical quantity. It is actually the relative speed of propagation of light in different media. The speed of light in different media is actually different. Speed of light or the propagation of light in vacuum is the maximum. That is 3 into 10 raised to 8 meter per second. In air, it is almost equal to vacuum, little bit less. It considerably reduces in glass, then in water, in alcohol, in ice, in turpentine, and so on. So in different media, the speed of light is different. The value of refractive index for a given pair of media depends upon the speed of light in the two media. But that is known as relative refractive index. But generally we are using absolute refractive index. Absolute refractive index means the ratio of speed of light in air or vacuum to the speed of light in any other medium. Speed of light in air is denoted by c, refractive index is denoted by n, and speed of light in the medium is denoted by v. Now suppose if we have two different media, then for medium 1 we'll take v1, for medium 2 we'll take v2. Here refractive index of two different media, or we can say relative refractive index formula is given. Refractive index of medium 2 with respect to medium 1 will be speed of light in medium 1 upon speed of light in medium 2. You can also write it as n21 is equal to v1 upon v2. Again, refractive index of medium 1 with respect to refractive index of medium 2 will be speed of light in medium 2 upon speed of light in medium 1. Or you can write n12 is equal to v2 upon v1. For absolute refractive index, the formula will be n is equal to speed of light in air upon speed of light in the particular medium, which is equal to c upon v. In your textbook, a table is given which shows absolute refractive index of some material media: air, ice, water, alcohol, kerosene, fused quartz, turpentine oil, benzene, crown glass, and many other. So you need to study that table, but it is only for information. No need to learn all the values. Now we'll move to next topic, that is spherical lenses. We have already done spherical mirrors, and here we are doing spherical lenses. Spherical lenses are formed by joining two spherical mirrors. You can see here, two spherical mirrors are joined. Here also two spherical mirrors are joined. Now if the spherical lens is thick in the middle and thin at the edges, and both the sides of a spherical lens are bulged outside, then such type of spherical lens is called as convex lens. And convex lens is also called as converging lens, because the rays of light will get converged over here. Now if the lens is thin in the middle and thick at the edges, and both the sides are towards the inner area, then such type of lens is known as concave lens. And this concave lens is also known as diverging lens, because the rays of light get diverged over here. Let us study image formation for both the lenses. First we'll study image formation by a convex lens for different positions of the object. The table is given here. It is also given in the textbook. So let us study one by one. Let's say the image of the object is at infinity. The position of the image will be at the principal focus. Here also the terms are almost same here, but you have to remember that because this is made up of two mirrors, it has two focal lengths, f1 and f2. 2f1 is actually center of curvature, that is c1. 2f2 is the center of curvature for the other lens, that is c2. So these are the differences, rest everything is same. Instead of pole, it will be O, that is optical center. Aperture is here, that is the length, mn, and rest everything is same. So if the object is at infinity, then these are the rays that are coming from infinity. The rays that come from the infinity are always parallel. So here the parallel rays are coming, they are getting refracted and they are meeting at opposite side on the focus, principal focus. So this is the first case. Now here you can see that the image is point-like, it is highly diminished, point-like, it is real, and it is inverted. Second case, the position of the object is beyond 2f, that means beyond center of curvature. So the image will be formed between f and 2f, between focus and center of curvature. The nature of the image will be real, inverted, and diminished. This is the case, second case. Here you can see this is center of curvature 2f1. The object is placed beyond center of curvature. When the rays come towards the lens, they get refracted and they meet between f2 and 2f2, that is between focus and between center of curvature. Here you can see the image has been formed. This image is smaller in size as compared to the object. It is inverted and it is real. Third case, if the position of object is 2f, the image will be formed at 2f on the opposite sides. This image will be real, inverted and equal to the size of the object. Here you can see the object is present at 2f1 and the image is formed at 2f2. Object is having certain height, the image is having the similar height. Fourth case, object is present between f and 2f. So the image is formed beyond 2f. This image is real, it is inverted and it will be magnified. That means it will be bigger than the object. This is the fourth case. Here the object is present between 2f1, that is C1, and between f1. The rays come towards the lens, it gets refracted and they meet beyond 2f2 or beyond C2. Here the image is bigger than that of the object. Case number 5, the object is placed at principal focus, so the image will be placed at infinity. This image will be real, inverted and extremely magnified, as you can see in spotlights. So here is the object. The image is formed beyond 2f2, it is formed at infinity. So you cannot see the rays meeting over here. Sixth case is between the optical center and the principal focus. The image is formed on the same side as that of object. Now this image, because it is forming on the same side, it will be virtual, it will be erect and it will be magnified. As you can see in magnifying glasses, eye lenses for short-sightedness. This one. Here the object is very small, the image is extremely magnified and it is present on the same side. That's why it is virtual image. Now let us study image formation by concave lens. In concave lens, we have to study two cases. First case is the position of the object is at infinity. Here, this one, here the object is placed at infinity, so the rays that are coming here are parallel. The image will be formed at principal focus, f1. This image will be point-like, highly diminished image, and this will be virtual and erect. Second case is the object is present between infinity and the optical center O of the lens. So anywhere it can be present. Between infinity and O, at 2f2, at f1, it can be present anywhere. The image will be present between f1 and the optical center. Here you can see this is the image A-B'. This image is diminished, small in size, but it is virtual and erect. So we have studied the image formation by a convex lens and a concave lens. Now sign convention for a lens. It is similar to the sign convention for a mirror. This is the center of the lens. Towards the right side, positive. On the upper side, positive. Towards the left side, it will be negative, and on the lower side, it will be negative. Here you have to remember that for convex lens, the focal length of convex lens will be positive on this side. The focal length of concave lens will be negative, that is on this side, left side. As we have done mirror formula, here we have to do lens formula. The alphabets, the symbols written here V, U and F are similar to the symbols that we have already studied in mirror. V stands for image distance, U is for the object distance and F denotes the focal length. Lens formula is slightly different than mirror formula. Lens formula is 1 upon V minus 1 upon U is equal to 1 upon F, whereas mirror formula was 1 upon V plus 1 upon U is equal to 1 upon F. So here there is a difference between the lens formula and mirror formula. The magnification will be height of the image, that is H dash upon height of the object, that is H. Or you can also write it as V upon U. In mirror it was minus V upon U, but for lens it is V upon U. So here we have completed the lens and mirror both. Another topic is power of a lens. What is this power of a lens? Power of a lens denotes the reciprocal of focal length of a lens. It also denotes the degree of convergence or divergence of light rays achieved by a lens. We all know and we have studied that ability of a lens is to converge or diverge light rays, and this ability actually depends on the focal length. A convex lens of short focal length will bend the light rays through large angles by focusing them closer to the optical center. And similarly, the concave lens of very short focal length will cause higher divergence than the one with longer focal length. So this property of divergence and convergence is known as power. The power of lens is defined as the reciprocal of its focal length. It is represented by a letter P, as you can see here. The formula is P is equal to 1 upon F, that is P is equal to 1 upon focal length. The SI unit of power is diopter and it is denoted by a capital D. 1 diopter is the power of a lens whose focal length is 1 meter. And you also have to remember that power of a convex lens is positive and power of a concave lens is negative. Opticians prescribe corrective lenses indicating their powers. And this power of a lens is actually important for those people who have defects in their eyes. Either they have nearsightedness or farsightedness. The optician will prescribe them particular lenses. So here we complete our chapter, that is light, reflection and refraction. Now if you have any doubts, you can contact me. Until that, keep studying and stay safe.